Hello, welcome again in the pure and genuine material under FFBMD. Only name is fake, but everything inside this channel is shining like a diamond. Let's start. Now our next topic is equilibrium of a particle. If net external force on the particle is zero, then particle is in equilibrium. According to the first law, this means that the particle is either at rest or in uniform motion. If two forces F1 and F2 acts on a particle, then equilibrium requires the sum of these two forces must be equal to vector sum of these two forces must be equal to 0. That is, F1 plus F2 equals to 0. The situation is shown in this figure. Here a particle is shown. One force is acting along this direction, another force is acting along this direction. This force must be equal in magnitude but opposite in direction acting on this particle. So we can write F1 equals to minus F2 vector. Second case, equilibrium under three congruent forces F1, F2 and F3 requires that the vector sum of the three forces is 0. Congruent means the force acting along a point. Here three forces are in equilibrium and these three forces acting along this point. One along this direction, one along this direction and one along this direction. Now because particle is in equilibrium, then their vector sum must be equal to 0. So then we can write F1 plus F2 plus F3 equals to 0. Similarly, if there are n forces, then for equilibrium requires F1 plus F2 plus F3 plus dash 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 Fn equals to 0. The situation is shown as a closed polygon of n sides made of vectors F1, F2, F3, F4. whose resultant is equals to 0. Now this can be written as sigma I equals to 1 to n f5 vector equals to 0. Now again this equation can be written in component form, that is taking this forces into x, y and z direction. That is, in component form, F1 vector can be written as F1x into I cap plus F1y into j cap plus F1z k cap plus similarly F2x I cap, F2y j cap, F2z k cap plus dash 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 Fnx I cap, Fny j cap, Fnz k cap, where I, j, k are the unit vectors along x-axis, y-axis and z-axis respectively, and here F1x represents the first force along x direction. Similarly, F1y represents first force F1 force along y direction. Similarly, F1z represents F1 force along z direction. Similarly, others can be taken, and which is finally equal to 0. Now this can be written as arranging. After arranging this, now above equation can be written as that this imply F1x plus, now we are taking the coefficient of I at one place, j at one place and k at one place. So F1x plus F2x plus dash 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 Fnx into I cap plus F1y to F2y plus dash dash Fny j cap Similarly, F1z plus F2z plus dash Fnz into k cap equals to 0. So equating the coefficient of I, j and k equals to 0, we have f1x plus f2x plus dash fnx equals to 0. This implies sigma fx equals to 0. That is, all sum of all forces acting along x direction must be 0 to satisfy the condition of equilibrium. Similarly, f1y plus f2y plus f2z fny equals to 0. This implies sigma fy equals to 0. That is, all forces acting along y direction must be 0 to satisfy the equilibrium condition. Similarly, f1z plus f2z plus dash fnz equals to 0. Sigma fz equals to 0. This sigma means summation fz. This is the representation. This symbol represents the sum of terms. Okay, this is a mathematical representation equals to 0. This tells that if there are several forces acting on a body and body is in equilibrium, then forces along all forces acting along x direction, along y direction and along z direction must be equal to sum of all forces acting along y direction, x direction, z direction must be equal to 0. For example, here find the value of theta taking g equals to 10 meter per second square and neglect the mass of the rope. Here a situation is shown in which we have to find the angle of theta. The situation is that a rope, a mass is hanged with a rope and a force at point P is acting along this direction, and the body P, point P and body mass of body 6 kg in equilibrium, that is in rest. Then we have to calculate the value of theta, and other values are given. That is the range, this length from here to here is given 1 meter. Again, this length from here to here is given 1 meter, and the force acting in this direction is 50 Newton. This problem can be solved very easily drawing the free body diagram of point P and mass 6 kg. So first you know what is free body diagram. The free body diagram is that diagram which shows all forces acting on the body. That is, all forces showing on the body is represented by free body diagram. Here we have drawn the free body diagram. Let tension T1 is acting along this in this string, and tension T2 is acting in this string. Then the free body diagram is shown in the figure. That is, T1 is acting in this direction, T2 is acting for this body, this is acting in this direction, and for P it is acting in downward direction. Force F is acting in this direction. Now we can decompose T1 into two component form. So T1 in this direction will be T1 cos theta, and in this direction will be T1 sin theta. Again, for this body, T2 is acting along this direction and weight is acting along this direction. So let what happen. Now we have a FBD of point P. Here the point P is shown. FBD of point P is shown. On this point, T1 cos theta acting in this direction, 50 Newton force is acting in this direction, T1 sin theta is acting in this direction, and T2 is acting in this direction. Now the point P is in equilibrium. So force along this axis must be equal to 0, and force along this axis must be equal to 0. Now using sign convention we can write, for example, sigma fx equals to 0. That is, force along x-axis must be all forces, sum of all forces acting along x-axis must be 0. That is, because T1 sin theta is acting in this direction, so using sign convention, minus T1 sin theta, and this will be positive, plus 50 equals to 0, or 50 Newton equals to T1 sin theta, equation 1. Along again sigma Fy, that is all forces acting along this direction must, sum of all forces acting along this direction must be 0. So sigma Fy equals to 0. Now this will be positive and this will be negative. So T1 cos theta minus T2 equals to 0. This gives T1 cos theta equals to T2, equation 2. Now again draw the FBD of block, that is mass 6 kg. For this FBD of this body, we have here shown T2 is acting along upward direction and weight is acting in downward direction. So for this body we can write sigma Fy equals to 0. From this we get T2 minus 60 equals to 0. This implies T2 equals to 60 Newton. Equation 3. Using 3 in 2 we get T1 cos theta equals to 60 Newton. This implies T1 60 and equals to T1 cos theta, equation 4. Now 1 by 4, that is equation 1 divided by 4 gives 15 Newton by 60 Newton equals to T1 sin theta by T2 cos theta equals to tan theta. This implies tan theta equals to 5 by 6. This implies theta equals to tan inverse 5 by 6 equals to 40 degree. Answer. Free body diagram FBD. It is the diagram showing all forces on a body or a system or a point. Force. Force. It is the external cause which changes the previous state of a body or a system or a point, or have tendency to change it. There are fundamental forces in nature. There are 4 fundamental forces in nature. First one is gravitational, electromagnetic, weak and strong forces. Now force can be divided into 3 part according to their property. The first one is field force, because gravitational, weight, electrostatic, magnetic, these are field force. Because this force act without coming in contact. Attachment, that is tension, spring force, these are called attachment force. And third is contact force, like normal reaction, friction, viscous force. Because these forces are acting along the surface or normal to the surface. For acting these forces, the body must be in contact. Question. Draw the FBD of block. Here one block is here shown, which is put on the table, and here A and B block is tied to the string which is hanging on the wheel ring, and here also a block is placed on the inclined surface. Now we have to draw and all these blocks are in equilibrium. We have to draw the free body diagram. So it is let you do it yourself. Question. Define these forces: weight, tension, spring force, normal reaction. Answer A. Weight. It is the force, gravitational, by which the earth attracts any body. The situation is shown in figure here. Earth, a body is here. Now earth will attack this body toward its center, and so this force arises, and this force is called weight or gravitational force by earth, and its value will be W equals to mg if the mass of body is m and g is the acceleration due to gravity, and unit will be kg weight, that is 1 kg weight equals to 9.8 Newton. 9.8 Newton. Keep this in your mind. 1 kg weight is equals to 9.8 Newton. The another next, tension. It is the restoring force developed in the stretch inextensible strings. It acts along the string in outward direction from the body connected to it. So the force acting in the string when a string is stretched is called tension. For example, a body is hanged with a string as shown in the figure. Then a tension will arise in this string. Now it will act in outward direction. For this body, the outward direction is in this direction. So for this body, tension is acting along this, and for clamp here, the tension will be acting in this direction. Similarly, in this case, for this body, tension acts in this direction. For this body, tension acts in this direction. For pulley, tension act in this direction, and in here tension acts in this direction. A spring force. This force arises when a spring is stretched on compressed or compressed along the length. It acts opposite to the elongation and compression. It is given by Fs vector equals to minus k into x vector. For one dimensional, Fs equals to minus k into x, where x is the elongation or compression in the string. The situation is shown in the figure. The x0 or x0 is the natural length of a spring. When we stretch or compress this, then a force will arise in the spring to oppose this compression and extension, and that force is called a spring force. Here, this is in this figure, the situation is shown when there is extension in a spring, because F applied is acting in this direction, a force is acting in this direction. So a spring force will arise in this spring in this direction, and the end point of a spring stretched by a distance x. Similarly, in this case, the spring is compressed to in this direction, so a spring force will act in this direction. So we can say that in a spring force always acts along opposite. A spring force always acts opposite to the extension and compression. Now here K is the spring constant or a stiffness or force constant. K is called a spring constant or a stiffness or force constant. And the reaction force, there are two types of reaction forces equal to the normal reaction plus friction force, or R vector equals to N vector plus F vector. Reaction force acts in the case of friction force. When friction force acts, friction, it is the contact force which acts along the surface in contact. It arises when A. There is applied force on any body whose surfaces are in contact. B. There is a relative motion between the surfaces in contact. C. There is tendency of the motion. The three situation is shown in the figure. First one, we are applying a force on a block which is placed on a surface, then there will start to act a force of friction opposite to this block or opposite to the relative motion. Again, another situation is shown in this figure. A block is moving with constant speed on the surface, so a force will act opposite the relative motion between surface and surface in this direction. Similarly, here the body has tendency to slip on the inclined surface, so force of friction is acting along this direction. Now, static friction. It is the friction force acting on a body when it is in rest. It is a self-adjustable but limiting. The situation can be discussed as shown in the figure. When consider a block is placed on a surface or any ground or any table surface. Now when we start to apply a force and slowly we are increasing force, then a force arises between the surface to oppose this applied force. As we increase the applied force, the force of friction, and that force which arises between the surface is called friction force. And as we increase the applied force, the friction force also starts to increase. The situation is shown in this figure. The body is in rest. Here we have applied 3 Newton force and body is not moving. That means there is also a friction force acting in opposite direction between the surface. So the body is in equilibrium. The situation here shown. 1 Newton, then we have applied 2 Newton, again body is not moving. Now the friction force will be of 2 Newton. That is at we increases the applied force, friction force also increases, but at times reach when friction force maximum, and at time after increasing a little force, after that limit the body start to move, and that limiting case is called, at that limiting case the friction force arises between the surface is called limiting friction. Later again we have applied force F equals to 3 Newton, and again body is in equilibrium. Now when we applied a little force more than 3 Newton, the body starts to move. Then this friction force, at that time the friction force acting on the surface will be called limiting friction. Here the limiting friction is 3 Newton in this case. And after when body start to move, the force a little bit decreases, frictional force little bit decreases, and during the motion the friction force acting on the body is called kinetic friction. Here this case is shown. Now limiting friction or maximum static friction. The maximum static friction acting on a body is called limiting friction, that is Fs max equals to Fl. For the situation discussed earlier, we have shown that when applied force becomes more than 3 Newton, body starts to move. And if applied force is 3 Newton and less than 3 Newton, the body does not move. So the here limiting force will be equal to the applied force, and that is 3 Newton. And this maximum static force, because body is in rest, and at that time the friction force acting on the body will be limiting force, because this is the maximum static friction, and this will be called Fl. Now normal reaction. It is the contact force acting perpendicular to the surface in contact. Consider a body block is placed on the table. Then table will apply a force on the block in upward direction, and block will apply a force perpendicularly in the downward direction. These forces are called normal force. Here the situation is shown in the figure. A normal force is acting on the body in upward direction due to table surface, and a block is applying force on the table in downward direction, which is downward direction, and these are equal in magnitude but opposite in direction. Experimentally, it is found that the limiting friction on a body is independent of area in contact and depends only on the normal force, that is FL proportional to N. This implies FL equals to mu s into N, where mu s is a constant of proportionality depending only on the nature of the surfaces in contact. The constant mu s is called the coefficient of static friction. Mu s is a dimensionless and unitless constant. Static friction is always less than equal to the limiting friction, that is maximum static friction. That is, in mathematical form, Fs is less than equal to Fl equals to Fs max, because Fs max is the Fl, or this implies Fs less than equal to mu s into N. Now friction force always opposes the impending relative motion or actual relative motion between the surfaces in contact.